Hi everyone, and welcome to the first of 4 videos where we're going to be looking at some past exam questions on 2 different topics actually. We're going to look at some questions that involve rate concentration graphs and some questions that involve some questions about the rate determining step. Now the reason that I've joined those 2 topics together is because usually both of those topics are kind of grafted onto the end of a standard sort of orders of reaction rate equation type question. You don't tend to get a whole question just on one of those topics. And you'll see that as we go through these questions that the majority of the question is hopefully familiar to you. And then there's one little aspect of the question that involves the new topics. So if we have a look at this question here, the first part of this question is actually nothing to do with rates. It's just asking us to balance this equation. So looking at this, you can see we've got 3 oxygens over here. So I'm going to need to have 3 waters there. And therefore now I've got 6 hydrogens, so I'm going to need to put a 6 here. And then I've got 2 bromines over here and 2 bromines there. So that seems like it's balanced. But this often catches people out, this question. I often use this question in lessons for this reason. It looks like it's balanced, but it's not balanced because what we haven't done is we haven't balanced the charges. Okay, you can see that on this side of the equation, there's no charge, nothing has a charge here. Whereas on this side of the equation, I've got 2 negative charges and 6 positive charges. So it's not balanced. Okay, I've got overall 4 positive charge here and no charge at all here. So this doesn't work. So in order to, I've got 6 positive charges. I don't really want to change that because that's going to mess up what we've already done. So in order to end up with 6 negative charges here, I'm going to have 5 bromide ions. So then the charges on this side are balanced, but I've now unbalanced the bromines. I've now got 6 bromines in total, so I need to put a 3 here. Okay, and now the equation's actually balanced because we've balanced the atoms and we've balanced the charges. Okay, then we get on to the actual rates part of this question, and you can see, as we mentioned, we've got a rate against concentration graph. Okay, so this is just for one of the reactants, and then the rest of the information has been given to us in a table, and hopefully you're familiar with this from some of the earlier videos about looking at orders of reaction. So they've done some experiments and this is their data. Fine. What do we actually need to do for this question? Okay. Using the results from the experiments, what conclusions can be drawn about the kinetics of this reaction? Kinetics is the fancy word for anything to do with rates of reaction. And then we need to calculate the rate constant. Okay. And again, I think we mentioned this in one of the earlier videos. You should make it clear how your conclusions fit with the experimental results. Okay. So first of all, let's have a look at this graph. Okay. So we can tell the order of reaction just from the shape of the graph. Okay. We do need to check what graph it is. Okay. We've already talked about concentration time graphs in some of the earlier videos. So just check the axis to have a look. Go, yeah, this is a rate against concentration graph. Okay. So what I'm going to say here then is that for BrO3 minus, the rate concentration graph, in contrast to the questions about concentration time graphs, where we said we have to actually work out the half-lives, you can't just look at the graph and decide what's going on. The rate concentration graphs for different orders of reaction are all completely different shapes. So we can just tell by looking at it what the order of reaction is, and it's important that you get familiar with this. So we need to describe what's going on with this graph. The rate concentration graph, what does it look like, is a straight line. Okay. But more important than that, it's also a straight line that goes through the origin, and you must mention this. Okay. From your maths knowledge, hopefully you're aware that if you have a straight line through the origin, what that tells you is that the 2 variables are directly proportional to each other. Okay. It's a straight line through the origin showing that the concentration of BrO3 minus is directly proportional to the rate. And if the concentration of the chemical is directly proportional to the rate, it means that it's first order. Okay, so the order with respect to the BrO3 minus is first order. Okay. Then for the other reactants, we're going to have a look at our table. Okay, and we've seen this in previous questions. So we're going to ignore the BrO3 minus because we know what's going on with that. And anyway, as you can see, the concentration isn't changing, so we don't need to worry about that one. If we look at the Br minus, we can see that between these two experiments, the concentration has doubled and the concentration of H plus has stayed the same. Remember, that's what we're looking for. We want to see where only one of the reactants has actually changed. And hopefully you can see that the rate has also doubled. Okay. So if we then say, I'll just do this in bullet points to make it clear. So if we then say from experiments 1 and 2, they're not actually numbered here. So we can just do that. We could do that in our question. It makes it clear to the examiner what we're doing. So from experiments 1 and 2, the concentration of Br minus is times 2, and the rate times 2. Therefore, the order with respect to the Br minus is first order. Okay, and then we want to do the same thing for our H plus. So again, here we want to find two experiments where only one of the concentrations has changed. So here, what I want to do, I want to keep the concentration of Br minus the same. So we're going to look here at experiments 1 and 3. Okay, we're going to say, look, that has stayed the same. From experiment 1 to 3, the concentration of H plus has been times by 2. And what has happened to the rate? Hopefully you can see that this has been multiplied by 4. And again, if you can't see that just by looking at it, you can always put these numbers into the calculator. Okay, and it will undo it for you. So if the concentration of H plus has been multiplied by 2 and the rate has been multiplied by 4, that's telling us that the H plus must be second order, right? Because the rate has changed by the factor of the concentration squared. So if we go back to here, we can fill this in from experiments 1 and 3. And we do need to make clear how it fits with the experimental result, so it is worth writing this out. The concentration of H plus is times by 2, and the rate is times by 4. Therefore, the order with respect to the H plus is second order. And it is important that you go through this process. You can't just say, this is first order, this is first order, this is second order. You do need to show where you've got that from. Okay. Why are we doing this? So we've made some conclusions about the kinetics. We now want to calculate the rate constant, okay, which hopefully you're familiar with this by now. But if we're going to calculate the rate constant, we need to write the rate equation. Okay. So rate equation is always in the form rate equals K. Don't forget about putting K in the equation. And then the concentrations of each of the reactants depending on what order they are. Okay, so we said that the BrO3 minus was first order, so that's going to be to the power of 1. The Br minus was first order, so that's also to the power of 1. And the H plus we said was second order, so that's going to be squared. If we want to calculate K, we're going to have to rearrange this. So K is going to be equal to the rate divided by all of those concentrations. And then we need to substitute in some of the values, okay? And it doesn't matter where we get those values from, as long as we don't mix and match them between the different experiments. So if we go back to our table here, I'm just going to use experiment 1, doesn't matter which one I choose. So the rate from experiment 1 is 1.19 times 10 to the minus 5. Put this so you can see what I'm doing. Then the concentration of BrO3 minus is 5 times 10 to the minus 2. The concentration of Br minus is 1.5 times 10 to the minus 1. And the concentration of H plus is 3.1 times 10 to the minus 1, but that needs to be squared. Okay. And so then we're just going to put that into the calculator and see what it comes out as. Again, personally, I would always do the bottom bit first, but it depends, whatever works for you really. So we'll do that one squared times 1.5 times 10 to the minus 1 times 5 times 10 to the minus 2. And then we'll do 1.19 times 10 to the minus 5 divided by what we just worked out. Okay, and we get a value of, does it say anything about significant figures in this question? Let's just have a look before we write this down. Doesn't mention it at all, so we don't need to worry. So the value that I've got here is 0.0165. We can leave it like that. It's not specifying anything about significant figures. We could put this in standard form, but we don't need to, so we could call this 1.65 times 10 to the minus 2. But we haven't got any units, yeah, so we always need to work out the units. It does actually say in this question that we need to work out the units. Sometimes they will say that, sometimes they won't, but you always need to do it. Remember, for units, we're going to substitute units into this equation instead of substituting in the values. Okay, so we're going to have moles per decimeter cubed per second for rate, and then moles per decimeter cubed for the concentrations. And again, don't forget to do the one for the H plus squared. It's very easy to miss that off. We can cancel out one set of moles per decimeter cubed and turn this into seconds to the minus 1 over moles per decimeter cubed to the power of 3 overall. Then, because it's on the bottom of the fraction, we can say it's moles per decimeter cubed to the power of minus 3. And then we need to sort this bracket out. So we can then say that the units would be seconds to the minus 1, moles to the minus 3. And remember, we multiply these powers, so it would be decimeters to the power of 9. And I think we've mentioned this before, that's fine, but the standard way of writing it would be to put the positive power first. Okay. You can see here this question is worth 9 marks. This is a question from the old specification, but I still use these questions because the chemistry, you will still need to do all these things. On the new specification, the longest question I've seen is worth 6 marks, which essentially means you're still going to have to do all of this, but you're only going to get 6 marks for it, which is a bit of a shame. But the knowledge and the way that you go through the questions are still the same.